is it the case that code is only for apps and websites? Clearly not. So what else could it be? And what else could it be for you? We can start to use code in more social contexts. We can start to use code to express ourselves and share ideas and formalize our ideas in new ways that we never had before. And that's only possible if more people accept that this is a fabulous tool for sharing and communicating a new way of representing language.
Sam tours the world as a live coder. He's constantly all over. I call him the Fat Boy Slim of live coding. And I think we should just welcome Sam. Sam, thank you.
You're an audience that already knows what live coding is that true? Who doesn't know what live coding is? Perfect. So that's it. So when I show a picture like this, everyone obviously understands what the context is here, although this particular musician's using his iPhone to trigger the strings, which is strange. He said it had a nice texture and he was playing with it. But this is a concert in Dresden a few weeks ago. And it was funny because the night before I was headlining an Algorave set. So this is in Karlsruhe, so at 12 o'clock at night. I was headlining this Algorave set in a nightclub, making dance music. And then 5:30 the next morning, which is quite unfortunate, I was on the ICE, the ICE train, across to Dresden, where I was doing a performance with this chap. And so it was really nice as he's doing this and I'm doing a bit of this. And we're both playing together and we're both improvising. I think the most exciting thing is that, that this instrument is extremely expensive. How much do one of these cost? Like, it's farcically expensive. And I'm playing with this thing, which is only 35 euros or 30 pounds. So there's a huge gulf of difference. Okay, the keyboard's quite fancy, it's about 80 pounds, but relative to the, that's cheaper than the stool of the piano. And the goal really is, from my perspective, is to perform, to make music, to enjoy myself, to be able to improvise, to be able to perform with others, so to be able to actually have the ability to be on stage and do a performance, a duet performance, where we're able to look at each other, able to see what's going on. We're actually, in this case, we're both projecting our screens. I'm projecting the screen of the Raspberry Pi, and he's got a camera looking down on his keys, and that's being projected as well. So the audience is able to see both perspectives concurrently. And so the goal really is to try and enable this kind of collaboration, but also to lower the barrier to entry for everybody. The goal really is, like, in a piano, the barrier is very low in terms of being able to just go up and approach the instruments and to start making some sounds, because anyone could just hit the keys and whack stuff and make some sounds, and it's sort of fun. My 3-year-old son can do this. Gregor can do it as an expert pianist. And what's the difference is that the amount of practice you put in can produce a range of different qualities of sounds or a range of styles of performances. But of course, one of the barriers to entry is the cost of these things and the size of these things. Gregor can't carry this around in his pocket. He has to tune it up particularly. In fact, what was interesting is when we first started practicing, he said, "Sam, what's happening in classical music is all funny. Everything's going a bit higher in pitch. So this piano is tuned slightly higher than the sort of 440 for A. Can you tune your Raspberry Pi to change it?" It's like, "Of course I can, yes." So we did a tuning session, which was quite fun. But yeah, of course, then, and it was also extremely expensive, whereas the stuff I'm doing is very portable, very cheap and accessible for everybody in terms of price. Then the real challenge then is that this weird instrument has a very strange interface. I mean, I'm showing you this keyboard. Where's the picture of the keyboard? Here. But obviously, it doesn't correlate directly to what's happening on the piano. If you've all seen live coding systems, I'm not hitting the keys and each key represents a note like a piano, or one key represents sustain. I'm actually typing a language in, and the language is the interface. And so the interesting thing here is that language also a barrier to entry? And I think it is a massive barrier to entry for most people. Most people don't know what programming is, let alone are able to understand different kinds of programming languages. And of course, different programming languages have different affordances. So I was told that most of you are media students, and I'm sure you understand that in media, different sort of mediums have different affordances. They're able to emphasize and de-emphasize. They're able to distort in different ways through different lenses the kind of information they're portraying. And it's an important thing to understand, not just about what information is being communicated, but how is it communicated, and to see those two things as a combination, a thing which is almost inseparable. It's the same with programming languages. we might be able to portray information in a programming language, and we might have these notions like Turing Completeness, which says that if I have a language A which is Turing complete, a language B which is Turing complete, then anything I can express in this language, I can also express in this language. It's a very philosophical statement to make. And like early mathematicians, logicians, programmers would love to make these kind of statements. And still, in many cases, particularly at Cambridge Computer Labs, they're still doing these kind of statements. What is computable? What is representable? How do I represent it? These kind of questions are really important to ask. How long does it take for this computation to happen? Is it solvable or not solvable? Can I prove this? Can I not prove this? These are interesting statements to make from a mathematical perspective, but we all understand, I hope, in a really sort of tacit way, that even though I can represent information in language A, and I can represent the same language representation in language B, it's not necessarily has the same affordances. It's not as easy to consume, it's not as easy to understand. It might have different distortions, different ways of thinking about it. And programming languages are identical. And I think what's really important is to start to think about that as part of the interface as well, and that about how we sort of consume and consider programming language. And when we look at the traditional programming languages for industry, and similarly, although it's not as similar at all, when we look at the traditional programming language for live coding, they're very much languages designed by engineers for engineers, right? So like when Thor talked about my previous system, Overtone, this was me, PhD in computer science, who'd worked as a sort of professional programmer for a number of years, sitting down and thinking, I've seen this live coding stuff, it looks pretty cool. What is the most powerful live coding system I could possibly build? And what would be the most exciting language to work with? How could I leverage that language to give me the best set of operational semantics, to give me the largest number of controls, and for each of those controls to be able to give me as much leverage in terms of modifying the system as possible. So Overtone was born with that in mind. What is the most powerful system I could build? And it did remarkably well, and still is used by many hundreds of people, thousands of people, I think, actually. It's one of the most popular Clojure projects on GitHub. Lots and lots of those star things. Everyone likes it. I made a band, and I toured the world live coding with this band, and it was very successful from that perspective. And it was, for my mind, this is the direction I was going to head in. Like, I'm going to keep developing this language, keep improving it, really focusing on it. Then, as Thor also said, there was an opportunity to work on an educational system which worked on the Raspberry Pi. And this was an exciting opportunity to build something very simple that I thought maybe would be a stepping stone towards something like Overtone. That someone would pick up a very simple system, work with it a little bit, and when they really got to the edges of it and they reached its boundaries, they would say, what's exciting, what's next? And Overtone would be one of the many options. SuperCollider language as well would be one of many. Tidal, lots of these cool systems. And so I set out to build a system. And this system looked a bit like this, right? So we have an environment which is just actually it wasn't black, it was white, but the black looks a bit cooler, I think. So we'll stick with the black. And the idea was you'd write the simplest thing you could possibly imagine to make a sound. So you would write the word play, and then you would choose a number to play, like number 80, and then you would hit play and it would make a sound. There we are, done. So this would be your first program. So this is all in my head, right? Because what I'm trying to do in this stage is not actually about live coding systems. It's not really about music, although we'll get to this very soon. What this was about computer science in schools. How do we teach computer science? How do we get kids engaged in computer science? How do we focus on ways to communicate the different constructs in computer science? So luckily in the UK, we have this new curriculum for computer science in schools, which is fabulous. We're leading the world in many ways in this area, although the funding behind it is massively lacking. But still, the curriculum is there. And I was reading the curriculum, I was thinking, how do I map this onto a set of lessons? I was collaborating with a teacher. I went into a school and taught this Sonic Pi stuff and developed it in the classroom. And what was really interesting is I had this idea of, wouldn't it be cool to make it, being able to make a melody really simple? So you could write play 80, I could sleep for 1 second and then play 85 and sleep for, I don't know, half a second. This is all the idea was, and then play for, I don't know, whatever note I wanted. Right, so you can see here the different notes are represented as MIDI numbers, but the children don't need to know about that. They don't need to know about music. All they need to know is, I ask this question all the time, and no one seems to be able to answer it. It's quite funny. What do numbers do? Does anyone know what numbers do? You're all university people, and none of you know what numbers do. Yes, right, that's the first time anyone's actually given me a sensible answer to this question. Yes, they go up and they go down, that's it. And the cool thing about things which have properties like they go up and go down is in computer science, we can use those properties to map them onto other properties. We can draw a relationship. We use this funny word called abstraction to describe this. And so what in music can go up and can go down? Sorry? Pitch, exactly. So, I mean, this is an obvious thing, right? And I'm explaining it to you in really simple terms. But when we go into schools and we're teaching children, we have to explain in these really simple terms. We can't go in, we expect them to have a prior knowledge of pitch and notation and chords and any of this stuff, right? We can't expect any of this. All we can expect is that when they write the number 80, it makes a note, and when it goes higher, the note goes higher. And then when it goes lower, oh, that's really much higher, and it goes lower, right? They don't need to know what 70 means. They don't need to know this is like tuned in equal temperament and it's matched the note on the piano, or the not Gregor's piano, obviously, because it's slightly higher tuned. They don't need to know that. All they need to know is that they can go up and go down. And that's the great thing, is that if they don't like this note, do you want a higher note or a lower note? And of course, they can also, if they want to be silly, like, what happens if I can do this? Of course, this also works as well. Slightly detuned between 70 and 71. So when you go into a school, you just teach abstraction. Already with one line, we've already taught abstraction. We've already taught the fact that this is maps on a concept in the real world, and they can also start to play with it with just one line of code. And then, of course, if we want to make a melody, well, at this point, we're not making a melody. We're teaching computer science, so we want to make a program. What does a program do in imperative languages? We do a sequence of instructions. Do instruction A, then instruction B, then C, then D, in order. So as we saw before, a lovely melody. It looks a bit like this. And then we have this melody. We can start to understand as a program of sequence operations. Now, what I found really exciting about this is that with these two commands, got pretty much all of Western notation, which is pretty exciting, right? So kids can take any musical tune that they like, and they can represent it with this notation. So they're taking tracks from Frozen, Twinkle Twinkle Little Star, Star Wars themes, and they're writing it with plays and sleeps, and they can have a lot of fun. So already we're able to engage children. Now I'm going to talk about three things in this whole talk as if they're the same thing, although you probably would want to discretize them quite clearly and concretely, but to me they really flow into each other. Those three things are education, the arts, and technology. And in these three things, I'm talking about education specifically, but the technology behind this, actually, at the moment is very simple, but we'll go into details of where that's not the case. But we're also talking about the arts. We're making music at this point, or we're making a program. What is the difference? Does it matter that there's a difference? Of course, it matters if you're in a computer science lesson, but what I found really interesting is that although initially there was friction about bringing the arts into technology, when the teachers were able to observe the engagement of the students, they thought this was fabulous. Like, oh, this is great. Little Johnny, he's always spinning around on his chair, but now he's completely focused. I've never seen Johnny so focused on anything before. Look at this. And so the music was able to engage them in ways that perhaps programming, had it been traditionally taught, hadn't. Now, what was interesting to me was that a lot of the exciting materials that have been created by the examiner boards in the UK had titles like "Give Binary a Try." Does that entice you? Are you all you want to stop listening to this talk now and go and give binary a try? What would you do with it? How would you try it? Like, okay, I'll give it a try. What is this? Is this good enough? Well, like, okay, what do I do with that? Now, okay, now the exciting thing is you need to think about. You could do some really cool things with this, but you need to know what those cool things are. So just giving it's like saying give numbers a try, you know, or give. I don't know, what else would it be? Like, give letters a try. Letters on their own, aren't they exciting? It's when you combine them to make words, or you put them on a piece of paper and you use them as symbols and layer them. You can do all sorts of cool things with letters. But it's not the letters which are intrinsically interesting, unless you're a weird person like I am. I think that's intrinsically interesting, but I don't think that if we're trying to engage a broader audience, we should focus on the people who are weird like me, who just find numbers in their own right interesting. We should be finding ways to attach an association between things like numbers and their real lives, which is why I think the music example is much more interesting. Oh, the other example was have fun, which is already a good start. Have fun with sorting. Have fun with sorting. So like this is one of the things, like as if you're a programmer, sorting algorithms are really exciting. There's lots of different styles with different affordances in terms of time and space. But who gives a monkeys about sorting? Like who in their real lives really cares about sorting their socks? Not me, and not lots of kids, I don't think. So we need to find better ways to engage children, which is why I think the arts is a fabulous thing. And of course now, what's really exciting is we can start to use the technology. So we go from going from the education to the arts technology. I can start to actually do things that music notation can't do very, very easily. Well, this notation can do this. I can say, let's just repeat this section 4 times. This is pretty cool. But what happens if I want to do this? Like number of times equals some range random value, which is an integer, between 5 and 10. Right? I don't know how many times it's going to play. That's quite exciting. Now instead of saying 4, I can say num times. Num times dot times. So maybe I just use the word num. I can start to create these names myself. And oh, look what's this happening here? I've just made a decision then about communicating something to you by changing the words. Like semantically, the program didn't change, but I'm concerned about what am I communicating to you. This is something that composers, when they're writing with Western notation, have to write above and below the score, with words. It's not in the score. But here, this is my score. And I can actually start to put abstractions and put communication and ideas in the score itself, which I think is pretty fabulous. So if I want to communicate ideas, I don't have to have an aside notation. It is part of the score. It's inseparable. So at this point, I can now say, well, I can play it a number of times. It's not going to sound very nice. So let's make it really fast. Everything sounds better when you speed it up. So let's use BPM 300. Right, there we are, done. So I've repeated my thing some random number of times. You can see the output, but I've got my composition. And the cool thing now is that this, even though it's using randomization in my system, this is completely deterministic, which means that when I run it again, it's going to choose exactly the same random number. So although it's random, it's not random. Because there's no such thing as random in computers. Everyone pretends there is, there isn't. What it is, it's like it seems to be random. It's chaotic enough that it appears to be random. If you want real random numbers, you want to sort of get some white noise from the space, or you want to actually have a human throwing a dice or something like this, And there's a real interesting thing about encryption and entropy, and these are all exciting things. And if you want good encryption, you need good randomization. But if you want to make music, I would say, I think it's more important to have reproducibility. Because now I can email this to somebody, and they'll hear exactly the same beautiful piece. I'm sure you'll agree that was a fabulously beautiful piece. So even though I'm using randomization, it is deterministic. It will repeat. It will choose the same things. I can show you this very clearly. If I say print rand, you can see here on the right-hand side, that's my random value. So rand will return a value between 0 and 1. Here I'm returning 0.5006103, whatever. If I call it again, I get the same number, and the same number, and the same number, and the same number forever. So it's not random, it's repeatedly random. But if I print 2 random numbers, where am I going? Or maybe 3, you'll see that they are different in time. So the first, what really is happening here is, imagine I was to roll a dice 10,000 times. It would take a long time, and I'd write down all the dice rolls. Right? And here I'm just returning the first roll of the dice, the second roll of the dice, and the third roll of the dice. When I run the program again, I return the first roll of dice, the second roll of dice, and the third roll of dice. They're the same values. So I'm just repeating the pre-rolled dice. That's all I'm doing. And this starts to become really interesting in terms of reproducibility. Now, that was a small sidetrack. But now at this point now, we've actually got a composition. And the great thing about this is that nothing in here I haven't taught a 10-year-old in 3 hours. Which is pretty exciting, right? It means a 10-year-old to pick this up, and more. There's much more I can show you, and I will. But in 3 hours, they picked it up. And what they're doing is they're not really programming, they're exploring sounds. They happen to be programming at the same time. And so there's a real conflation between education here and technology and the arts. They're all really combined. And what's really exciting is people start asking questions like, and they did, which has completely surprised me because I wasn't expecting it at all. I have my melody, Sam. I can do this lovely melody. Where is it? Oh, no, and let's repeat this just with 2 times. Let's do it 8 times. Right? And I have another 5 times where I'm playing a sample with a bass drum. And I want to play them at the same time. So I run the code. Oh, I've got the melody. I've got the bass drum, right? How do I play them at the same time? So this is an interesting question where the arts led the technology. And the computer science curriculum does not cover playing 2 things at the same time. It's considered an extremely advanced topic. But the kids wanted to know it. So why not teach them? And because it meant that they would carry on. So I built a very simple system which allowed them just to wrap something. There's something called in-thread, which no one ever uses anymore because I've built something way cooler, which I'll show you. But what in-thread does, so the way to think about it is that, before I show you in-thread, and this is how I explain it to the children, it's like a relay race programming. You have this baton, you pass it on to line 1, line 1 does something, changes the speed, pass to line 2, which is blank, which passes to line 3, which passes to line 4, which then says, I want to do something 8 times, so that's great. So we go 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 5, 6, 7, 8 times, and then we go down to 11, then 12, and then do this 5 times, and we finish the race, and we hand the baton to the official, and we're finished, okay? So we just have a single person running through the code, just running from instruction to instruction to instruction. But of course, if we want to do 2 things at the same time, we need 2 people to be running at the same time. So this in-thread mechanism, what it really does is that when the person gets to line 3, they sort of magically divide into 2 people. They sort of fork off. And now have one person now running between 4 and 9, 8 times, and then finishing. And then another person exactly at the same time running between 13 and 16, and then finishing. So I'm splitting the race into 2 directions. And so this allows me then to play those 2 things at the same time. If I don't play it so ridiculously fast. You can hear them at the same time. So this is a way to get concurrency, and the kids were loving this. This was great. And of course, we're teaching all the basic computer science skills. We've got iterations and instructions and function calls. We're also teaching university-level things. This is called a thread. It's a university-level topic, typically. But I'm teaching this in 10-year-old in primary schools, and they're totally getting it. Does this make sense? By the way, you can ask questions at any time. If I say anything you don't quite understand,
one quick question.
yes.
Does it support Go?
Does it support goto? So the question is, could I have an instruction here which explicitly said go to line 9, for example? No, it doesn't. No. It's a shame. That's interesting. We should discuss why that's a shame later. I think actually that it's easy to be able to reason about these things without it jumping around in random places. But it could be quite interesting to be able to do that from a musical perspective. There would be some interesting byproducts of that kind of behavior. But anyway, no, it doesn't. So yes, so does this make sense so far? Do you understand what's going on here? Does anyone not understand this code? Because it's absolutely fine not to, and I'll just spend a little more time explaining it. Does anyone not understand this? You're not programmers, I guess. How many of you are programmers? Oh, a few, right, okay. Okay, but the non-programmers, does this make sense in any kind of way? You see that this weird thread thing is probably the most complicated thing you've seen in programming, but all it is it says, take the runner and split them into 2. One runner goes to line 4, and one runner goes to the end of the end. Comes here. Yes?
So the sleep, timing of the sleep relates to the BPM?
Yes.
Not some abstract second.
No, so that's a good thing. So this, again, it's like when you're teaching in schools, you start off by saying that sleep for 1 means sleep for 1 second. Sleep for half means sleep for half a second. So you're not teaching them about musical concepts. It works really well. But then there's always a few children who really get it very quickly. And they'll ask questions like, how do I play note C? Or how do I make this faster or slower? And so for those people, the Sonic Pi supports extensions, which aren't necessarily in the curriculum or in the lesson plans, but they're little sneaky things you can give the children to give them a bit of a boost to keep their engagement. And so, yes, the BPM thing, it modifies all the sleep times. So we're actually sleeping for 1 beat, not 1 second. The default BPM is 60, which makes it 1 second. And the notes, for example, if they say, I don't want to, what the hell's note 80? I want to play note C octave 5, that also works as well. And so, again, some children already know musical notation, in which case you just use that. But I think if we start the lesson by saying you need to know musical notation, you need to know what BPM means, you're adding barriers to entry. So This is about having tools to give the children who already know these things a way of using their knowledge already, but not requiring that to engage in the lesson plan at all. So yes, and then we have actually lesson plans for teaching computer science and also music. We did a project where we use this to teach music lessons available. So if you've got any friends who are teachers who want to start using this kind of tool in their schools today, we have lesson plans to support that now. But let's continue this journey. So once we've got these things, what I found was quite interesting, this is from a technical perspective now, it was when we had this threading thing, the way I had implemented this was using a standard mechanism. This sleep is a standard programming mechanism which says sleep for at least 1 second. Not for exactly 1 second, but at least 1 second, perhaps more. Because typically in programming, what I care about is that if I want to do job, you're this way around, so job B here, right? I might want to make sure job A is done first. Right? So what I'll do is I'll sleep until job A is done, then I can start job B. So all I care about is the ordering works. If it takes longer or shorter, that's fine. All I care about is that I don't start B until A is completed. That's typically what you care about when you're making programs. When you're making music, it doesn't make sense, right? Because I want to happen on the beats. I don't want to start the snare drum and when the cymbal's finished. I want to start it exactly the same time, perhaps, or I want to start it before, or I want to have my own ideas about time, which is not about topological ordering of jobs. But when you implement this kind of system with traditional programming constructs, like the traditional sleep, what actually happens is that, well, not only does this actually end up sleeping for 1 point some delta, and those deltas add up, which causes drift, this play thing actually takes real time to execute. The computer has to run some instructions. The computer doesn't run infinitely fast. And on a Raspberry Pi, especially the original one, that takes quite a considerable amount of time relative to, say, this fast Mac. And so if I have a bunch of these plays, well, this takes roughly four times as long as a single instruction. And so all those times start adding up and you get huge drift. So if you're interested in this kind of stuff, I've written a paper which describes this modeling thing. But I'm only explaining it to you because I'm just trying to make the point that traditional programming constructs and concepts don't necessarily directly apply to artistic contexts. And what's important for engineering and for business isn't necessarily important for making music. And so I then, and this is interesting, when you're writing one program and do this, you never notice this drift. It's very hard for you to perceive it, unless you play it simultaneously to something else with very, very good timing. But when you've got multiple threads going around, you have like a bass drum playing and a melody playing, you soon start to hear it sounds absolutely awful because these things are out of synchronization. And the human ear is very good at hearing this difference of synchronization. So this is an important way the technology needs to then modify itself to keep up with the arts. So in Sonic Pi, now, the sleep is a very special sleep. And it always makes sure that the time is exactly right. Right? If you're interested to know why, I'll spend time talking to you afterwards, or you can read the paper. But I don't want to go into too much detail about technical things right now. But it's important to say that sometimes we have to re-implement things and re-change things and readdress and redesign. Even the basics, like a sleep command, has to change to be able to map different domains. So now, in Sonic Pi, this sleep works perfectly. Everything's completely in time, which is great. But one thing to try and engage people, and in ways that is interesting, is that I wanted to be able to start to reproduce the work I was doing with Overtone. Because I wanted to be able to go into a school and just do a little bit of a performance. Like, hey, look, kids, if you practice this, you can do this too. Right? And so at the moment, I've got a tool for composition. I can make a melody, and I can loop things and construct things. So I could imagine writing a bit more of a sophisticated thing using the same construct to make a nice melody. And of course, I can do lots of other crazy things like change the length of the notes and change the rate of the samples and change the cutoff values, and I can show those in a moment. But what I really wanted to do is to do a performance, and that starts to become quite complex. So I invented this thing, because really a great way of doing a performance is to do something like this. Have these two things. Now I need to use this weird in thread. There we are, we're off. We have some basic starting points, but then I want to be able to change part of this and have it be able to be modified. Now, the really interesting thing about, from a philosophical perspective, loops is they're really, really rubbish, to be honest. They have this beautiful, like, simple trait, which is they just go round and round and round and round and round and round and round forever. But once a program gets into a loop, it can't get out. It's like a black hole, right? So the program is just trapped inside this loop, which means if I want to change it, I can't because it's not coming out of the loop. I have no option to say, actually, can you now go over there, please? Because it's not. I can't speak to it. It's trapped in this loop. So I need a way to be able to have ability to change it. So I invented a new concept in programming, and I call it the live loop. And you just say live. And I need to give them both the name live. And again, this is born purely to try and teach children. I mean, I can show you how to do this using the constructs I've already shown you in one extra thing, but it starts becoming very complicated. And I can't go into a class and say, these are all things you need to learn. So live loops need one extra thing. And the way to think about them is they're like performers on stage. I've got a band. So I'm going to have like Claire doing the melody, and Steve bashing the drums. Okay, right. So I give them names. And now we have the same behavior as before, a loop. Notice I didn't have to put the in-thread nonsense, so I can get rid of that now. So you can pretend you didn't even know that existed. But it's doing the same thing. What it's actually saying is, with a live loop, it's going to play the same time as any other live loop. They're going to work at the same time. Because they're different people. They have their own agency. But the cool thing is now, I can go and say to Claire, can you stop playing the horrible beep sound? Can you play something different? So use synth, blade. And so Steve, can you make the cutoff a bit lower? Oh. And maybe play it a bit slower. Right? So, and I change it on the fly without having to do anything special. All I was doing is changing a few numbers, adding a few things. And notice how the beat hasn't stopped. So I can now sort of bring the... like fade in the cutoff, right? And all I'm doing is changing the code and hitting the run button. Oh, you haven't seen that. I've hidden that from you. This is also what the children see, these special buttons at the top, which are really nice. So the run button is the button you press to run the code. I was doing it with the shortcut. It's a bit more clunky to press the buttons, but yeah. So at this point now, what I find really interesting is that we've already broken away from the curriculum of computer science. We're teaching concurrency, teaching multiple things, which is not what we should be teaching. And then we're also teaching this liveness, changing the code on the fly. If I talk to normal engineers about this, they're like, you're nuts. You should never do this. This is not a safe thing to do. It's a crazy thing to do, right? How can you prove your system does exactly what it should do? And it's like, well, I don't care. All I care is I can change them. I'm not building a system for flying aeroplanes. I'm building a system for making music. And also I'm building a system to try and capture the imagination and to maintain the engagement of children in a classroom. And I don't give a monkey's about if it works correctly. What do I care about? It has this playfulness. And I'm able to tinker with it and change it. And I'm able to have a very fast feedback cycle between a modification and hearing those changes. So this tool provides me exactly the ability to do that. Does this make sense so far? Are you with it? I have no idea how long I've got to talk for and what time it is.
Probably got about 10 minutes left.
Yeah. So I think, yes, okay. So so at this point now, I'll skip to ideas about adding some more music features to this system, because I'd like to show, well, I'll show you this later, but I'll very quickly show you that. And then I'll spend time asking questions. I think that's probably the best thing to do. But I guess the whole thing I'm trying to describe is that when we silo people into technology, I'm from the computer labs. I'm a technical person. It's just nuts. Like combining the technology and the arts and the education has allowed me to come up with a concept like this, which has provided people around the world with a very, very low barrier to entry to having a creative experience with code. And I'm seeing lots of people starting to do performances. I'm seeing a lot of children putting their compositions up on the internet and sharing their work. And also, what we've got here is text as an interface, which is, I guess, if you've seen live coding systems, is not new to you. But this is text as an interface that 10-year-old children can understand, which I think is really exciting. Because if a 10-year-old child can understand it, then a 70-year-old person can. And I have users of Sonic Pi who are in their late 70s, who are translating old Baroque pieces of classical music into Sonic Pi and then playing it back, and I'm really excited that they can do it, and they have this newfound power, which is all what it's all about. A couple of more things to show you. If I wanted to add some reverb, this is something very hard in traditional live coding languages. I've got to teach a lot of concepts. In Sonic Pi, I just need to say where I'd like the reverb to start and where I'd like the reverb to end. And I can change the room size. Maybe I want some echo as well. So again, with some very simple constructs. Okay, this might look alien if you've never seen code before, or if you've never seen Sonic Pi before, but trust me that 10-year-old kids could understand this in a few hours. Although actually that doesn't help you, because 10-year-old children have much more elastic minds, and they've kept their minds open. And it's really frustrating teaching adults, because they sort of say, no, I don't get computers and I never will. It's like, you really could if you just opened your mind. So yeah, what we've got here is this sort of nested thing. So this play goes through the echo, goes through the reverb, and then goes out to the sound card. So it's a bit like chaining guitar effects pedals. And I'm also, in the same way with guitar pedals, I can change the knobs. Here I can change the knobs here, and each of these things has many different knobs to manipulate. So that makes a lot of sense to me. Yeah, so I think I'll stop. If you want me to do a little performance, I can do that, or I can also ask questions, or I can do both. Yeah, little performance? I normally stand up for performances, but I can't need this low chair. So shall I do something? So what do you want? What kind of music would you like? Dancey, ambienty, strange, glitchy, crunchy, distortion-y? Strange, right, okay. What I normally start with is, I always quite like this. This is a sample here. And I quite like this because it shows how just one sample can sound quite nice, right? And we can start manipulating one sample and we can do interesting things. So all I'm doing is triggering a sample. At some point it's going to stop. Right, so before it stops, I can trigger it again. But I can also overlay them. If I run another one, it overlays it, so I'm actually having multiple at the same time. So I can change the pitch of it. So what I'm trying to show you is that with one line of code, you can already have a lot of fun. Sometimes I might want to have that sample played with the same sample twice. This is the chord. And maybe to accentuate one of these pieces, I might slice it in and out. So. And then if I want to make sure that things are in time with each other, rather than pressing run button every time to start it, I can put this in a live loop. Of course, now I need to tell it how long to wait, so I'm going to sleep for maybe 16. And then I need to make sure the code is correct, because I need to give it a name. Foo. So now I've got enough pieces to actually start really performing, because if I don't do anything, it's just going to play the same thing again and again. So I have time to decide what to do next. So maybe I'll put that like this. His speakers can't handle the boom. Well, this is the important part of live coding, because different environments have different qualities of speakers and different ways of reverberation. So you need to be able to listen to what's going on, and be able to adapt to it. So I'm sending you all to sleep now. So I'll try and, what can I do now? So I can throw in a bit of noise. What I'm doing is changing the rate. Reversing the rate makes it go backwards. And maybe add some vocals. So you can start to change the sound quite easily and quite effectively. And it's a clap. And so what I'm trying to explain is that by combining the arts, by combining the education and technology in new exciting ways, we can build systems that have new affordances. In this case, I have a system which I feel is one of the most creative, expressive tools I've ever worked with, but also as a tool I can use to go into schools and teach. I can also go to arts venues, like yesterday I was at the Junction in Cambridge, teaching adults how to use this system. And it was amazing to see what they came up with just after a couple of hours of playing with the system for the first time. So I really invite you to play around with this thing. But more importantly, I really like to invite you to reevaluate, Russ, change my language, reevaluate how you perceive code. Is it the case that code is only for apps and websites? Clearly not. So what else could it be? And what else could it be for you? And if you've already decided that code is for other people, for nerdy people who like to sit in their bedrooms and in dark rooms and just sit there looking at text, which actually is what I like to do, and a lot of people do, but it doesn't have to be like that. We can start to use code in more social contexts. We can start to use code to express ourselves and share ideas and formalize our ideas in new ways that we never had before. And that's only possible if more people accept that this is a fabulous tool for sharing and communicating and a new way of representing language, a new medium for communication. And so when more of you have an understanding of code, I have an ability to speak to more of you with a higher resolution. And I'm really, really looking forward to that time in the future. So please play with Sonic Pi, play with other systems. If you're interested in talking to me, this is my email address. Please email me and give me suggestions. That's too many A's. We're very happy to talk to you about any ideas, any thoughts you've got, any frustrations. Show this to your grandparents and to your children and to yourselves. Thank you very much.